Hello everyone. I'm not gonna lie, this is like my fourth time trying to record this question, but my mic keeps being like so weird. So let me just hope it locks in now. Anyway, step 2, question 4, 1998. This is also the 24th foundation module step question. So let's just get into it. The integral in is defined by in equals the integral from 0 to pi of half pi minus x sine nx plus half x cosec half x dx. When n is a positive integer, evaluate in minus 1. Hence, evaluate in, leaving your answer in the form of a sum. Cool. So the first thing I want to do here is, before we get in minus 1, let's just get in minus 1, which would be, we just substitute n minus 1. So because I just expanded n minus 1 x. And then as we can see here, this minus x plus a half x just becomes a half x. So this becomes now let's take this away from in. Well, we can see that both of these integrals have half pi minus x and cosec half x in common, so we can use that. Dx. Cool. So we want to simplify this part of the integral, and we can do that using the addition and subtraction formulae for angles. So using these formulae, we know that sine nx plus a half x is identical to sine nx cos a half x plus sine a half x cos nx. And then similarly, sine nx minus a half x is identical to sine nx cos a half x minus sine a half x cos nx. Cool. So since we want this minus this, so let's label this 1, that's 2. We want 1 minus 2. Well, first, sine nx cos a half x minus sine nx cos a half x is just 0. And then sine a half x cos nx minus sine half x cos nx would equal to sine nx. I mean, sine a half x cos nx. So now we substitute this back into our integral. In minus equals, let's take the 2 on the outside, so 2 times the integral from 0 to pi. Cosec a half x sine half x cos nx dx. Well, cosec is 1 over sine, so we can cancel cosec x multiplied by sine x, or cosec a half x multiplied by sine a half x, which will just equal 1. So this becomes 2 times the integral from 0 to pi half pi minus x cos nx dx. And now let's split this into two integrals by expanding the brackets. So this becomes pi multiplied by the integral from 0 to pi of cos nx, as you multiply this by half pi and then you take half pi out, and then minus the 2 times the integral from 0 to pi of x cos nx dx. Cool. So first, this integral, let's evaluate. This becomes pi multiplied by 1 over n. Pi multiplied by 1 over n sine nx from 0 to pi, or at pi sine nx is 0, and at 0 sine nx is 0. So this whole integral just equals 0. And now, so that means all of this equals minus 2 times the integral from 0 to pi of x cos nx dx. So now let's take the limits. So, oh no, we can't take the limits. Sorry. We have to do integration by parts, because this integral is the product of two functions. So a smart choice of u would be x, making du 1, and then that means dv is cos nx, and v is not minus 1 over n sine nx. That makes in minus 1 equal to uv from 0 to pi, which is x over n sine nx from 0 to pi. 2 times that. Minus 2 multiplied by minus this integral, which is just positive 2. So plus positive 2 multiplied by the integral from 0 to pi of v du. So 1 over n sine nx multiplied by 1, which is just that. And, well, this sine nx at pi is 0, at 0 is 0. So that would just equal 0. And then let's take out the 1 over n here. 2 over n multiplied by the integral from 0 to pi of sine nx dx. Let's evaluate the limits. So 2 over n minus 1 over n cos nx from 0 to pi. First, let's take out 1 over n, and then let's evaluate. So minus cos nx at pi would be minus cos pi x, and then at 0 cos nx would be 1, so minus 1 would be positive 1. Cool. Now to simplify this further, take the graph of cos x. So cos x, well, at 0, let's look at cos x at integer multiples of, this is n, my bad. Cos x at integer multiples of pi. So at 0, 1. At pi, it's minus 1. At 2 pi, it's 1. At 3 pi, it's minus 1. So you can see it alternates between minus 1 and 1 at even and odd values of n. So for the even values of n, is positive 1, and for all values of n is negative 1. So we can rewrite cos pi n as minus 1 to the power of n. Therefore, in minus 1 equals 2 over n squared, 1 minus 1 to the power of n. Cool. So now we figured out in. Asks us to hence evaluate in. So hence evaluate means that we need to use the previous part of the question, which is this. And our answer involves some form of sum. So there's a clever thing we can do here. We can notice that in plus in minus 1 minus in minus 2 plus in minus 2 minus in minus 3 plus ... and this continues to I1 minus I0 plus I0. So first, let's take this first part of the sum. So this would be the sum from when n equals 1 here to n equals n. Well, from an arbitrary value, so from k equals 1 to k equals n of this this equation that we found earlier in the question. So we can plus that I0 and n. So we can write that as the sum from k equals 1 to n of 2 over n squared, 1 minus 1 to the power of n plus I0. So we can factorize out 2 there. But now let's find out I0, which is simple. We just plug in to in. So what in is half pi minus x sine nx plus half x cosec half x. So if we plug in n equals 0, it would be half pi minus x sine half x cosec half x dx. And sine half x and cosec half x cancels out because they're reciprocals. So this becomes the integral from 0 to pi of half pi minus x dx. So that equals half pi x minus half minus half x squared from 0 to pi. Well, this becomes half pi squared minus half pi squared plus 0 minus 0. So I0 just equals 0. Therefore, I equals 2 multiplied by the sum from k equals 1 to n of 1 over n squared, 1 minus 1. Yeah. To the power of n. And there we go. That is in. Thank you for watching, everyone. Have a lovely day. Yeah, keep following the STEP project. We love the support. Yeah.